Hello everybody and welcome to the module on hyperparameter optimization. I'm Lars Kotov, and in this video we're going to talk about evolutionary algorithms. Evolutionary algorithms, as the name suggests, are inspired by evolution in nature and are based on relatively simple concepts. We are starting with an initial population of configurations, and then we repeat the following steps. We evaluate those configurations to judge their performance, in other words, to measure their fitness. This is the term that is usually used in the context of evolutionary algorithms. And then we apply two operations, crossover and mutation. For crossover, we take two configurations and we combine them, for example, by taking some hyperparameters from one and other hyperparameters from the other. And in mutation, we randomly change the hyperparameter values of a configuration. Then we take a subset of the configurations that we have generated in this way, and we promote them to the next generation, so we choose which ones will survive. Again, this is inspired by evolution, and we want the usually fittest individuals to be promoted to go on to the next generation so that overall the population improves. This does sound a little bit abstract, so let's have a more concrete look at what this might look like in the context of hyperparameter optimization and in the context of automated machine learning. So here's a more specific example. We randomly sample from our configuration space the initial population of hyperparameter configurations. This is essentially what we do in the random search that we have covered before, except we do a small number of evaluations there and we don't spend our entire budget on this step. Then we take the top performing half of these configurations, where top performing is defined really in whatever performance optimization criterion we choose. So this could be, for example, accuracy, and we apply the crossover and mutation operators. Crossover concretely might look like us taking two individuals, two configurations, and choosing the hyperparameter values from the first one, and the first half from the first individual and the second half from the second individual, and simply putting those together. Of course, we do have to be a little bit careful there with dependencies between hyperparameters, but this is something that we could fix if we accidentally introduce invalid hyperparameter configurations in this way. Mutation could look even easier, where we randomly choose a hyperparameter for the configuration that we want to mutate, and we apply Gaussian random noise centered around the current value. Becomes a little bit more difficult if we're talking about categorical hyperparameter values, but there we can make this work as well. So we apply crossover and mutation until we have generated the same number of configurations as in the previous population, and then we take that and we promote it to the next generation. And we simply repeat that until, for example, no further improvement is observed, or until we have exhausted our budget. So what does this actually concretely look like in practice? Let's have a look at the running example of XGBoost on OpenML dataset 11. So again, I have chosen my two hyperparameters lambda and alpha here. This graph is slightly different to what you have seen before, in that the accuracy is still encoded as the color here, but the size of the circle now shows you the number of the generation that we're in. And what we can see here is that, to start with, on this side of the graph we have a bunch of not so very good configurations, so we don't observe a good accuracy there. And this is of course what we would expect, because if we start with a random sample from our configuration space, then some of them will not perform well. But crucially, what you can see is that all of these circles here are relatively small, which means that they come from the first generation. And after that, so once we really start applying the evolutionary algorithm and once we start moving towards better performing configurations, all of them are actually better performing. So all of the large circles for the later generations are really clustered in this left-hand side for small values of alpha, left-hand side of the graph, in particular in the bottom left corner where we have small values of lambda and alpha, which is where we observe the overall best configuration. So we can really see that most of the later configurations, the big circles for the later generations, are clustered in this particular area, And this is, of course, exactly what we want, that we not only focus in on the areas of the configuration space where we do have the well-performing configurations, but we also, in later generations, once we have learned something about what happens in the configuration space, we don't go back to the areas where we have observed bad performance and do more evaluations there. So again, an example of an adaptive search, we do take what we have observed before into account when deciding where to evaluate next. And in this particular example here, this works really well by allowing us to focus within just a few generations, so relatively small example here, on the parts of the configuration space where we do observe good performance. Here are some considerations for evolutionary algorithms in practice. One of the advantages is that they're conceptually simple, although maybe not quite as simple as, for example, the local search that we have covered in the previous video, but overall it's still a relatively simple idea that nevertheless works pretty well in practice. It can also work with many different types of representations. So for example, we can optimize full machine learning pipelines with their individual components, and I've given you the reference on the slide here if you're interested in finding out more on that. It is, and I have already mentioned, an adaptive search. We don't blindly search. We don't do a lot of evaluations that we did not need to do because they are not getting us good performing configurations. And it's also relatively easily parallelizable. So for example, what we can do is we can take all the individuals within a population and we can evaluate them, we can assess their fitness independently and in parallel. This, of course, depends to some extent on the size of the population that we choose. If we have a very small population size, then we might have workers left over, so we might have resources that we cannot use because there's not enough potential for parallelism there, which brings me to the disadvantages, because applying evolutionary algorithms in practice is not entirely straightforward. There are many things that we need to decide, and I have glossed over a little bit of these before. We need to define the population size, I've already mentioned that, but we also need to define the number of generations. We, more importantly, need to define how crossover and mutation should be done, and this is similar to what we've talked about in the context of local search before, where we need to define what a neighborhood looks like, what a small change looks like. We need to define the relative frequency of crossover and mutation, what configurations we should take to generate survivors, and so on and so forth. So a lot of things that we need to decide before we can start applying evolutionary algorithms, and most of these in many cases will have a substantial impact in practice. So if I choose these incorrectly, then I might waste resources, I might not get a good configuration as I would have gotten otherwise, I might not get there as quickly as I would have gotten otherwise. So we do have to be a little bit careful, and you do have to have a reasonably good understanding of how all these considerations affect performance in practice when you want to apply evolutionary algorithms for hyperparameter optimization. In summary, evolutionary algorithms can improve configurations by combining known good performance and random changes. So this is the crossover and mutation that I have mentioned before. How exactly this works in practice is something that you would need to decide as the person who implements it. They can be applied to all types of configuration spaces, which makes them very flexible. This is an advantage over some of the more sophisticated methods that we will have a look at going forward. But nevertheless, they are not entirely straightforward to apply in practice because of all the different things that you need to decide and because of all the different settings that you need to adjust depending on the particular data set, in some cases even. So not as easy to apply as certainly grid search and random search, but also local search in practice.